So what you see here on the screen is a schematic of Young's double slit experiment. So this schematic shows you the two slits present here and here. So there are slits S1 and S2. Let me name them. The top one is S1, the bottom one is S2. The distance between these two slits is known. So maybe I have d distance between them, small d, and that's this much. And the light is allowed to go through only by these two slits. They have certain widths. We are not really concerned with the widths of these slits right now, but we are saying that they are enough to get enough light intensity on the other side so that we can see a pattern over there. And the distance between the slits and this guy is the screen where we watch the interference. So the distance between these two guys is big D. So there is a big D here, this much, and every point on the screen is going to receive light from both these sources. Of course, I'm talking about a reasonable distance on either side of the center of the screen. So this point, which is the center of the screen, I will mark it as O. This point is the center of the screen, and if I go to a small distance on one side of O or a small distance on the other side of O, I can say that there is a region where waves from S1 will be coming in and waves from S2 will be coming in, and what I will be seeing at that point is maybe the superposition of those two waves. So I have taken a point P, which is somewhere here, and this point P is at a distance y from O. So the distance from O to P is y, and I'm interested in probably knowing what is the net amplitude at P, what is the net intensity at P, provided I know what are the amplitudes going through slits S1 and S2. And on the left hand side of this apparatus, I have a certain arrangement with the help of which I am creating plane waves. So when I say plane waves, I mean waves that are traveling along a single axis, and the wavefronts are plane. So maybe if I take the right hand side axis as the plus x axis, then the waves are traveling along plus x axis, and the wavefronts will be all planes parallel to the yz plane. So let's just assume that there is a source of red light here. So you have waves coming in, and these waves will be going through S1 and S2. So the only way that these waves can reach the other side of this cardboard is by going through slits S1 and S2. They will first of all suffer a diffraction at S1, diffraction at S2, because of which they will start spreading, and the light from S1 will fall on a certain region on the screen here. The light from S2 will also fall on a certain region on the screen here, and the places where the lights from S1 and S2 overlap, there will be superposition, and the final intensity that you see will be obtained after doing a careful mathematical analysis. We have done a lot of that maths in class 11, so I'm not going to repeat that entire maths. I'm just going to take the final results from there, and then I'm going to proceed. So what are the things that we can do mathematically in this apparatus? We know that in order to find what happens at P, I should know the value of phase difference that exists at P between the two waves. So if there is one wave S1P coming in, and if there is another wave S2P coming in, then I have to find out what is the phase difference between them, and that is what will dictate what will be the net amplitude at P. So perhaps slit S1 lets out A1 amplitude and slit S2 lets out A2 amplitude. So you have A1 amplitude going from slit S1 and A2 amplitude going from slit S2, like that. And I want to figure out what is the net amplitude at P. You know the formula. The formula goes like A net whole square is equal to A1 square plus A2 square plus 2A1 A2 cos delta phi. We have seen this equation in class 11th. We have seen, in fact, the entire derivation of this equation too. So I'm not going to go into that. We need to find out this guy delta phi. Now this guy delta phi is related to the value of delta x. Delta x happens to be the path difference, and I know that delta phi can be found out by multiplying 2 pi by lambda with the value of delta x. And what is delta x? Delta x is the value of path difference, that is in order to reach this point P, one of the waves will be traveling a shorter path length and the other one will be traveling a longer path length. Now in this case, because point P is above point O, it's S2P which is traveling a longer distance and S1P which is traveling a shorter distance. But there may be a point below the center line of the apparatus here. So there may be a point somewhere here, and if I take a point somewhere here, then S1 to that point will be a longer distance and S2 to that point will be a shorter distance. So you have to take care of who is longer and who is shorter that way. So the value of delta x will be S2P minus S1P here. S2P minus S1P. Now how do we calculate S2P minus S1P? There are two equivalent ways of calculating S2P minus S1P, and I'm going to show you both of them. For the first one, what we will do is, in fact, the one that hits most of the students immediately after seeing this picture is about the Pythagoras theorem. So what they say is, maybe I can find out what is the distance from P up to some point here where I can draw horizontal up to S1, and what is the distance from P to a point here from where I can draw horizontal to S2, and then I can figure out the length of S2P and S1P using Pythagoras theorem and then find out the difference. Now that is all right, but the expression will be so difficult to simplify that we will not be able to proceed without making some assumptions, and those assumptions that we are going to make those assumptions that we are going to make are actually pretty reasonable assumptions because they relate to the size of this apparatus. Now usually when you go for a Young's experiment of this kind, we have seen that we get very good interference results if this distance small d is typically of the order of around 0.1 millimeters to 1 millimeter. And this guy, capital D, usually is of the order of let's say 1 meter to around 2 meters. And this distance y is again actually pretty small. Y is of the order of typically 1 centimeter, usually less than that, or maybe around at the maximum 1.5 to 2 centimeters, not more than that. So these are the distances that we are talking about. Now when I look at these distances and then I see what are the approximations I can make, the one that immediately strikes me is this: small d by capital D is going to be much smaller than 1. In fact, small d by capital D, if I take the largest value of small d, that is 1 millimeter, and if I take the smallest value of capital D, now in some cases they will say that this d is around 80 centimeters. Fine, ballpark, because I'm not saying that it is strictly 1 meter or more. It might be 80 centimeter, 85 centimeter, that is all right, but then this fraction will always be much smaller than 1. And for these values that I have shown you here, 1 millimeter divided by 1 meter is like 1 divided by 1000, which I know is in fact much smaller than 1. So my assumption is justified. The second assumption that I will make is this, that y divided by d is again very small. So y divided by d, sorry, not small d, this has to be capital D. Capital D here is much smaller than 1. Because again, this is like 1 to 2 centimeter, this is like 1 to 2 meters, so again a factor of around 100 coming in. So I take this value 1 centimeter, maybe I take 1 meter, there is 1 by 100 factor. Even though I take the largest value here, probably 2 centimeter, and the smallest one there 1 meter, I will still get around 1 by 50, which is much smaller than 1. It classifies as much smaller than 1. 1 by 50 will be roughly around what, 2%, and that's fine. So we will work with these assumptions, and under these assumptions there are now two different ways to figure out the value of S2P minus S1P. Let me show you the first one. So here is this apparatus again, and I know that the distance here is small d. Let me just mark out a few distances here. This distance will be y minus d by 2, because this entire distance is d, and half of that distance will be d by 2. So I can say that this entire distance from the point P to the lower slit is going to be y plus d by 2. And anyways, the distance between the slits and the screen was capital D. So let it be there. This is capital D. And you can simplify things. You can then say this is S1 and the lower slit is S2 and this point here is P. So therefore, using just basic maths, S2P minus S1P is going to be y plus d by 2. In fact, let me write d first. No big deal, I can write anything first, but d square plus y plus d by 2 whole square, and all this expression raised to the power half minus S1P will become big D square plus y minus d by 2 whole square, and all that raised to the power half. And how do I simplify this entire expression? What I will do is, I will first of all take big D out of both of these brackets and then apply binomial theorem. So all this will become equal to big D 1 plus y plus d by 2 whole square divided by d square, and all that is raised to the power half minus d times 1 plus y minus d by 2 by whole square divided by capital D square whole power half. And this looks like 1 plus x to the power n. So I can use the binomial theorem only if this entire term is much smaller than 1. And because of the assumptions that I have made, you see that y by d is much smaller than 1, small d by d is much smaller than 1. So it stands to reason that if I just take y and add d by 2 to it, that will still be much smaller than big D. And to top it all, I'm squaring that number. So squaring that number will make the effect even smaller. So this final end result is going to be much, if anything like that exists really in maths, then all that much smaller than 1. And this guy will also, it will also be all that much smaller than 1. So I can write this entire expression as D into 1 plus y plus d by 2 whole square divided by 2d square minus d times 1 plus y minus d by 2 whole square divided by 2d square. And after opening the brackets, you will see that the first d here in this bracket and the d here in this bracket are going to cancel off. Then I will get a term that will be y plus d by 2 whole square divided by, and this d will cancel out, so a 2d in the denominator. And here also I'm going to get this d going off with this 1d in the denominator, so I'll have 2d in the denominator. So let me take that common. I'm going to get 1 by 2d out, and what is left inside? Left inside is y plus d by 2 whole square, and there is a minus sign here to take care of, and so there is a minus here, and y minus d by 2 whole square. And you open up the brackets, you are going to get 1 by 2d, and inside the brackets you see you will have a y square here and a y square there, they will go off, a d square by 4 here and a d square by 4 there, they will also go off, and then there will be 2 times of y times d by 2, so there will be a yd term here, that is plus, and a yd term here in this bracket which is minus, but there's a minus outside, so that term will also become plus. So you have a yd plus a yd, so you've got a 2yd here overall, and what you're going to get is y small d by capital D. So this is the value of S2P minus S1P. So therefore delta x is equal to S2P minus S1P is equal to y d by d. But as you see, this is high on maths. In fact, just high on simplification skills. It's not big on physics, So why don't we find a better way to do this? And let me call this equation number 1, although I'm not going to arrive at this equation usually using this method. I'm going to use a different method, and that different method can be obtained by just taking this figure. So let me make physicists like, you know, approximations and then get to the answer. So now what I do is this. I remove these distances, they are hideous, you know, and what I say is this. Now given that this distance y is very small, it's known that the distance from point O to point P is y, and that is very small, and given that this distance d is also very small, what I can say is this. I can say that probably if this angle here is theta, then this angle here should also be theta, and this angle here should also be theta. Now that seems incredible. How can that be so? Visibly these angles are so far away, you know. This guy looks so tiny and this guy looks so big, but then you have to keep in mind that this is not the exact figure. Let me show you how I may scale up that figure. I have got a figure somewhere here that I was drawing. Yeah, maybe something like this. So what the figure might actually look like is something of this kind, and this is also not the actual figure, mind you. Now this is not the actual figure because what I'm doing is, see, these two red dots here on the left hand side are the two slits, S1 and S2. So I've got S1 on the top, S2 at the bottom. This is maybe P point, and this entire thing is this big D distance, and all I've done is I have actually brought the slits much closer, and I have marginally increased the value of this distance, and I have made this distance y smaller, and you can see that this angle theta being equal now starts making sense, because what you have here is some angle theta. Maybe I will draw that here first. So there is this angle theta, that green angle theta, which is also equal to this angle theta. No big deal, because they should be corresponding angles, parallel lines, and roughly you see that that will be equal to this green angle theta, that will also be equal to some green angle over here, and this is, mind you, not even the exact figure. If I have to draw the exact figure, then first what I have to do is maybe take these two red dots just 1 mm apart. So these are also too far apart, you know. Let me just show you on a scale how far apart these guys are. So maybe they are around 4 mm apart, as it looks like. So 3.5 to 4 mm apart. So the first thing that I need to do is I need to take them just 1 mm apart. So maybe I think I won't be able to manage it, but let's see. So one is this green dot here, the other is this other green dot here. So roughly 1 mm apart. I don't know whether you're able to see them or not. And once I take these guys 1 mm apart, I need to take my screen at least 1 meter away. So the other line which I have to draw, this orange line, should be not really here, because this is a very small distance. In fact, let me show you the extent of my screen. So you see how big is my screen, starting from the two green dots which I have, you know, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 centimeters. So maybe I'll have to scroll like 5 screens. So after I scroll 5 screens, I will draw this line, and on that line I will take a distance which is approximately the same. You see, this distance which I have taken is almost 1.5 centimeters. No, it is not 1.5, it is less than 1.5, it is 1.1 centimeters. So maybe I will take that much of a distance, because that's what I want, right? 1 to 2 centimeter. So I have to scroll 5 screens from these two green dots, and then I have to take a distance. Then I have to draw 2 straight lines from these 2 green dots to that point, whichever is the point after scrolling 5 screens. And I'm not even daring to do that. But if you have a really huge chart paper which you can fit on your entire study table, you are encouraged to do this activity and then see whether these thetas will be equal or not. So you will find out that these thetas will be approximately equal, and this angle, the one which is included between the two red lines here, is actually going to tend towards 0 degrees. It will be 0.1, it will be 0.05, who knows, you know. So this angle is going to be really small, people. This angle is going to be around, let's say some number, you know, 0.05 degrees, something of that. And I'm not going to really find out. Okay, but you know, we have a way to find out. So let's actually find it out. And let me erase these thetas here. I don't want that theta, I don't want that theta. They are just making the figure messier. So let me just draw the theta at the center and say that the thetas everywhere are going to be the same. Let me get a decent enough value of theta. So what do I know? I know that if I find tan of theta, that will be y by capital D. So tan of theta is going to be 1 centimeter divided by 1 meter, which is 1 by 100. So what is theta going to be typically? Theta is going to be, let me take my calculator, people. So tan inverse of 0.01, that gives me 0.5 degrees. So 0.5 degrees. So this angle theta itself is around 0.5 degrees. That's such a small angle, that will be a really small angle. And how big will that angle be? Can I have any idea about that angle? Yes. The way I can get that angle is this. Suppose I draw a line on the top. Suppose I draw a horizontal on the top, and I'm going to draw a blue horizontal somewhere here. Yeah, that's a horizontal line. Now if I call this angle as theta 1, then that entire angle becomes theta 1. That entire blue angle is theta 1. And then if I call this green angle here as theta 2, then this small angle here becomes theta 2. So the value of this angle that I'm looking at, angle S1 P S2 for the disbelievers, so I'm just trying to show you what this angle is. This is going to be theta 1 minus theta 2, and that will be. So how do I find out theta 1? Let me take a typical value of D. Typical value of D is around let us say 1 mm, a very large value. So half mm is here, and this is 1 centimeter. So 1 centimeter and half a millimeter, so that is 10.5 millimeters. So I've got 10.5 divided by D. So what do I have? Tan inverse of 10.5 divided by 1000. That is going to give me this entire angle theta 1, that's around 0.601 degrees, minus theta 2. So for theta 2 I need to take only that distance, so y minus d by 2. So y is around 1 centimeter, so 10 millimeters, minus 0.5 millimeters, so 9.5 millimeters. 9.5 millimeters divided by big D, which is around 1 meter, which is 1000 millimeters. So tan inverse of all that is 0.544 degrees. So that will be approximately what? Just a moment. 0.601 minus 0.544, and that will be around 0.057 degrees. So you see, this is the typical size of angles that we are dealing with. So tiny. So this angle here is around 0.05. So let me now remove those theta 1s and theta 2s. We don't need them anymore. Their job here is done. Gone. So once I have removed these small parts, now what do? So I have to figure out what is S2P minus S1P. So what I do is I drop a perpendicular from S1 onto this line, and let that be shown using this green line here. So maybe this is a perpendicular, seems almost like perpendicular. So this is the perpendicular from S1 to this point, to this line S2P, and let me call this point as Q. And I know that this angle here is exactly 90 degrees. I know the angle at Q is going to be exactly 90 because I have drawn a perpendicular. Now this angle is 90, this angle is around 0.0, it was 5 I took earlier, but now my bad, I'll take it as 0.06 degrees. So 0.06 degrees, people. And this angle here turns out to be 89.94 degrees. And that's so close to this angle 90. So what I approximately say is that this triangle S1PQ is isosceles. So what I claim is, that triangle S1 PQ is isosceles, and that claim is very much justified. So therefore S1P should be equal to QP, and therefore now S2P minus S1P can only be said to be S2Q. So therefore delta X is S2P minus S1P, which is S2P minus QP, which is S2Q. So I've got S2Q now that I have to find out. And how do I find out S2Q? This is again a part of a right angle triangle. Now if you look, the angle at Q is going to be 90 degrees. And in a right angle triangle, I know the hypotenuse. Maybe if I can figure out some angles. So how do I figure out those angles? Yeah, cool. The angle here was theta. So let me draw this green angle. This angle was theta. So the remaining angle here is 90 minus theta. And the angle here is theta. And now I've got what I wanted. I've got the value of hypotenuse. I've got the value of one angle. So approximately I can find out S2Q to be small d times sine theta. So therefore S2Q, which is equal to the part difference delta Q, is equal to d sine theta. But you see, theta itself is a very small angle. How small was theta? 0.5 degrees. I showed you that theta was 0.5 degrees. So for that much small angle, 0.5 degrees, sine theta will be approximately equal to theta, will be approximately equal to tan theta. So this is equal to d tan theta. And I can find out the value of tan theta in this triangle. Let me name some point here. Let me name it as maybe R or something in green color. So this point is R, the center point here. So in triangle RPO, this triangle, I can find out the value of tan theta. This is y by big D, and that's it. So therefore now I know. So therefore delta X is y times d by capital D. So this is another way to get it, and this is more physics like, So this is let's say equation number 1 again. They are the same equations, so 1 and 1. So now I have figured out what is delta X, and figuring out delta X will help me to figure out what is the value of phase difference at P, and the value of phase difference will allow me to figure out the net amplitude using this formula. So that's it. So now job done. So now I can figure out whatever is happening on the screen at all the places. But then I want to show you some standard results. So what are the standard results? Now the first question that I want to answer is, at what points on the screen will there be constructive interference? And anyone. Now I know that for there to be constructive interference at some points on the screen, the value of delta X should be equal to n times the wavelength, and that will give you n lambda is equal to, we have equation number 1 right here in front of us, y d by d. So y small d by capital D, and if you solve this for y, you are going to get n times lambda capital D by small d, and inserting different integer values for n will give you the values of y, where delta X will be equal to n lambda, and so where we are going to have constructive interference. So we will have constructive interference at those points on the screen where y is equal to 1 lambda d by d, 2 lambda d by d, 3 lambda d by d, and so on. And I call this lambda d by d number as beta, n beta, where beta, which is equal to lambda capital D by small d, is called the fringe width of the interference pattern. So let's keep that in mind. This is called the fringe width of the interference pattern. Now let us just try to draw that screen and see where are these points. So maybe I'll just give you a rough idea of where these points are. So you draw this screen and you see that if I take some center point somewhere, need not be at the center of this orange line that I have taken, because this orange line may be starting anywhere and finishing anywhere. So at some points, such as maybe A, maybe B, maybe C or something, which are at distances of beta, and then you have 2 beta, and then you are going to have 3 beta and so on. So these are, sorry, not 2, 3 for the last one. So 3 beta. So you see that the distances beta, 2 beta, 3 beta, etc. from the center line, from the center point of the screen will be such that there will be constructive interferences there. So at A there will be constructive interference, B there will be constructive interference, at C there will be constructive interference, and so on. Now similar question, so I'm just going to copy paste this, and I think you know the question. So at what points on the screen are we going to have destructive interference? So let me remove that and put destructive. And again we can do it in terms of the part difference. We know that for there to be destructive interference, the value of part difference should be equal to odd multiple of lambda by 2. And the odd number that I can choose can be either 2n plus 1 or 2n minus 1. I will choose a 2n minus 1 here, and you will understand the reason also shortly. So 2n minus 1 into lambda by 2. So therefore 2n minus 1 times lambda by 2 should be equated to y small d by capital D, or I'm going to get the values of y as 2n minus 1 by 2 into lambda big D by small d, which is 2n minus 1 by 2 times beta. And let's try to locate these points on the screen. So let's take the screen here and try to locate where those points will be. So let me say I'm going to now change my convention a bit. I'm going to represent as C any point where I'm going to have constructive interference, and as D where I'm going to have destructive interference. And in order to show you which of the interferences is that, whether it's the first destructive interference or the second one, I will use maybe a subscript, so D1, D2 or D3 or something like that. So maybe I'll take the center here at O somewhere. So the center is at O. Now at this point O, I don't know what is going to happen, we will see that afterwards. But then as I move away from O, to have a constructive interference I should go to a point that is beta away. So maybe I have a point C1, the first constructive interference, which is at a distance of beta from the screen. Now where will be the first destructive interference? What's the first odd number? The first odd number is 1. So beta by 2. So I know that there has to be a destructive interference somewhere here. So that I will call as D1. Then I know where will be the second destructive interference. I see this formula and I know the next odd number is going to be 3. So 3 by 2 beta, and I know that is here. So this is this is D2, and then above that should be C2. So I get the hint. I get the hint that I can have equidistant places of constructive and destructive interferences, and there will be a D3 here, and there will be a D4 after that, and so on. And the spacing between each location of constructive interference will be beta. Between each of the locations of destructive interference will be again beta, but between one destructive interference and the next constructive interference will be beta by 2. So now I know something about this interference pattern, and that is that the distance between Cn and Cn plus 1 is going to be beta, where this is the nth location of constructive interference. This is the n plus 1th location of constructive interference, that's beta. dn and dn plus 1 is again beta, that distance is again beta, and between dn and cn, that's beta by 2. So dn to cn, that is going to be beta by 2. And about the intensities, so we have seen all that much. Now few things remain. One is what happens at O, and what exactly will be the intensities at all these points, and how do we show a fringe here. We have called beta as the fringe width, so there should be something called a fringe whose width should be beta. But then exactly what is that fringe? How do I show that fringe here? Now after seeing the animation yesterday in the previous class, I think it will be amply clear to you what is that fringe width physically. So that's the width of that entire band which we saw in the previous class. And that's it. So now let me show you this apparatus again. Maybe I'll take this guy and try to see what happens at the midpoint O. So the question, what happens at O? So this is the figure which I have. Let me just throw away some unnecessary things. Maybe this point P, I don't need it. These two lines, I don't need them. They're gone. And this is also gone. And maybe that triangle should also go. Yeah. So fine. This is the clean figure which I have now. So if there has to be a superposition of two waves at this point O, then I have to locate which two waves are they. So one is obviously S1O, the other is S2O, and you will see that in the usual Young's double slit experiment, when the two waves reach point O, there is no delta x between them. They have reached O after traveling exactly equal lengths of path. So maybe I will just take a moment to, yeah, sounds fine. So this is one, and the other one is this, from S2 to this point. Yeah, and you will see that before hitting S1 and S2 we had a plane wave, and being a plane wave we knew that we had the wave fronts perpendicular to the direction of propagation of wave. So any point on the wave front is obtained by joining, each wave front is obtained by joining those points that have which are in the same phase and where the energy has reached at the same time starting from the source. So it stands to reason that they have traveled equal distances, and from S1 to O and from S2 to O again the distances are going to be equal. So the value of delta x at O is going to be 0. There is no path difference, and when there is 0 delta x, delta phi is also going to be 0, so the phase difference is also 0, and that is a very special case. So we are going to have a maxima here, of course. We are going to have constructive interference here. So please keep in mind that here onwards we will name the points of constructive interferences as maximas, or the constructive interference happens at those points which will be called maximas, and the destructive interference will happen at those points called the minimas. And at the center there is a special constructive interference where the phase difference and the path difference are exactly 0. At no other place of constructive interference are the phase difference and the path difference going to be 0. For example, I go to maybe C1, there is a constructive interference, but the value of phase difference is 2 pi. Now 2 pi is equivalent to 0, but it's not 0 really. C2, the phase difference is 4 pi. C3, it's 6 pi, and C4, it's 8 pi. They're not 0. but at O it will be 0, and so O has got a special name. O is called the central maxima. O is the so-called central maxima, and that is how we define central maxima, people. So please keep in mind that in the traditional Young's double slit experiment setup, we will have the central maxima at O, and this point O will be such that the value of part difference at this point is 0. But if I go for some non-traditional Young's double slit experiment settings, where I'm going to play around with this slit S1 or maybe this slit S2, so that at this point I no longer get the value of delta x is equal to 0, then I have to locate that point where delta x is 0, and that will be the new location of central maxima. So please keep in mind that central maxima is not the maxima that is there at the center. Central maxima is that maxima where delta x is 0. So central maxima is that maxima where delta x and delta phi are both 0. So please keep that in mind. So now what we are going to see is a bright patch at the center, then a dark patch here, then a very bright patch at C1 here, then a dark patch here, and so on. And I know that I don't have to explain the pattern because you have seen it in the previous class in that animation. But something about intensities. So what are the intensities? Now the question is, what are the intensities at maximas and minimas? So you can easily then guess. So at a maxima, let me do that here on the left hand side. At a maxima, the net amplitude square is going to be a1 square plus a2 square plus 2a1 a2, because I will have cos of either 0 or 2 pi or 4 pi or 6 pi something, and it will be 1. So this is a1 plus a2 whole square, and intensity at maxima is going to be proportional to the amplitude at maxima whole square, and this is the amplitude at maxima. So this same guy, I'm trying to write this guy as a max, and so intensity at a maxima will be proportional to, so therefore intensity at a maxima is proportional to a1 plus a2 whole square. And what happens at a minima? So that is probably here on the right hand side. So here at a minima, you can say a minimum square is going to be a1 square plus a2 square minus 2a1 a2, and this is going to be a1 minus a2 whole square. And so the intensity at a minima should be proportional to this guy a min square. So that means you're going to have I min proportional to a1 minus a2 whole square. So let's keep that in mind. Now at some point in time, they will ask you to find out the ratio of the maximum intensity to the minimum intensity. And from here it's very clear that I max to I min should be equal to a1 plus a2 whole square divided by a1 minus a2 whole square. So this is the entire expression. Now a few things to take away. How do I find out the values of a1 and a2? So that's again a big question. So a question here arises, what do a1 and a2 depend upon? So this is something which you have seen in these in those animations which I showed you. the amplitudes will depend upon the slit width. So if the slit is wide, it will allow a large amount of energy to go through, and I will say that because the amount of energy going through is large, the intensity is large, so the amplitude is also large. So usually what we will say is that the amplitude allowed by a slit is proportional to slit width. So if you have got a slit, if you have got perhaps a slit of width W that allows light to go through to the other side, then the amplitude going through A is going to be proportional to W raised to the power M, some number M, where usually I can take M as 1. So if they have specified what that M is, fine. If they have not specified, you just take amplitude to be proportional to width. And you say if I double the width, the amplitude going through is also doubled. So that means the intensity going through becomes 4 times. The total energy going through also becomes 4 times. So please keep that in mind. So it stands to reason that if you take equal widths, then A1 becomes equal to A2. So therefore, for slits of equal width, A1, so let me write it here itself, A1 will become equal to A2, and so I max will be proportional to 4A square and I min will be proportional to 0. In fact, I don't even have to write this symbol here. I can just say is equal to 0, because whatever is the constant of proportionality, when I multiply it by a 0, I will get the answer as 0. So I max to I min, first you will see that I max to I min will be infinite. This is 1. But all this is only when the two amplitudes are equal. So you have to bear that in mind. So only when the two amplitudes are equal, the minimas will have 0 intensity, which means they will be completely dark. So which means they are completely dark. But if the amplitudes are not equal, then the intensity at a minima will not be 0. It will be A1 minus A2 whole square. That means the minima will not be completely dark. There will be some brightness there even at a minima. Although that brightness will be less than every other part on the screen, but there will be some amount of lightness, brightness and light. My God, people, So please keep in mind that only when the slit widths are equal, or if they specify that the amplitudes that are being thrown out by the two slits are equal, then I min will be 0. You will get completely dark or pitch black dark fringes. Otherwise, you are not going to get pitch black dark fringes. No. Otherwise, you are going to get the least brightness at dark fringes, but there will still be some light over there. And in this case, when amplitude 1 is equal to amplitude 2, you can say that the maximum intensity, I max, is actually proportional to 4 times the intensity of, or the intensity supplied by each slit. Because if the amplitude that goes out of each slit is equal to A, then the, okay, I have not put a equality there. So let me say A1 is equal to A2 is equal to A. So you may be wondering what this A is. This A is their common value. But then if each slit sends out an amplitude A, then I can say that each slit sends out an intensity that is proportional to A square. And so I can write, instead of A square, intensity supplied by each slit. So the maximum intensity will be 4 times of that, and the minimum intensity will be 0. Yeah. So the next thing that we have to talk about, people, is about something called the coherent sources. Now, before we talk about what are these kind of sources, let's go for a small discussion. Let's see what is it that we get at P. How much is the intensity that we actually get at P? Now, the intensity that we get at P can be represented as intensity at P, that will be proportional to amplitude at P square, and amplitude at P square will be amplitude 1 square plus amplitude 2 square plus 2 amplitude 1 amplitude 2 cos delta phi. Fine. And we know that we can figure out what is the value of delta phi. We have done that before. Delta phi happens to be 2 pi by lambda times delta x. And we can find out the value of delta x. We have done that and so on. So, we are happy all in all. So now what we want to do is we want to have this experiment going on with maybe the yellow light of sodium. Now the yellow light of sodium is mostly monochromatic. We can talk of it as a monochromatic light. In fact, there are two wavelengths present in the yellow light of sodium. So there are the sodium lamps which we have, Sodium lamps, they emit two different wavelengths. There is a D1 line of sodium, I guess, which is 5890 angstroms. And there is a D2 line of sodium, which is 5896 angstroms, but they are very close to each other. So we are going to think of this light as mostly monochromatic. We are going to talk about it as monochromatic. And by now you have understood that all the experiments that we are doing here, Young's experiments, they are using monochromatic lights, light of a single color. So when we were doing those animations yesterday, you saw that I was always choosing a particular color and then doing that experiment. So monochromatic lights are what we need. So what we do is we take two sodium lamps, and let's ignore the small variation here. Let's say that this is just one wavelength, not a big change here between the wavelengths. So sodium lamps are going to emit one single wavelength, and let me keep one sodium lamp in front of S1, this one, and let me make this region opaque so that the light from this sodium lamp does not go to S2, and let me keep another sodium lamp in front of S2, and then let me try to see what happens at P. And surprisingly, what you will see is just an average intensity. You will not even see the interference pattern here. Now, why don't we see the interference pattern here if we use two sodium lamps like this? The answer, in fact, lies in the way light is produced. So the question is, how is light produced? Anyone? So you have to keep in mind, people, that light is produced during de-excitation of electrons. So electrons which were in a lower energy state were made to go into a higher energy state, and that excitation could be because of two reasons. Excitation of electrons can be caused either by giving them energy in the form of heat or by hitting them with appropriate energy photons. So the excitation of an electron into a higher energy level is either because of heat. So you heat up the substance and it keeps on gaining energy. The electrons, they get energy, they go into the higher orbits, higher energy states. When they come back, they emit light. Or maybe you supply exactly a specific photon with a certain amount of energy that can lead to excitation of which can lead to excitation of an electron from a lower energy level to a higher energy level. And then when the electrons, they jump back down to the lower energy level, they release another photon of the same wavelength perhaps, but then it can also be in many stages, so leading to many different photons. So excitation can be affected either by heat or photons, but the de-excitation always leads to release of a photon, and that is what is light. So when you look at our sun, and the sun has got nuclear fusion going on inside it, nuclear fusion really only creates a large amount of energy. That large amount of energy heats up the elements of which the sun is made up of, and when those elements are heated up, the electrons, they get excited, then they get de-excited, and during the de-excitation, the light that they generate is the one that we get. The bulbs that you use, the tungsten bulbs, you heat up the filament. When you heat up the filament, the electrons get excited, and they again de-excite. They go into the lower energy state, and then they emit light. So it is during de-excitation of electrons. Now de-excitation leads to release of photons. Right. So de-excitation of electrons will lead to release of photons, and there are two sodium vapor lamps here. In one of those sodium vapor lamps, and of course we take a very small amount of sodium vapor, but that will also have billions and billions of atoms. And here also in the other one there will be billions and billions of atoms. And what will happen is that due to all those random electron de-excitations, because of course when you have billions and billions of atoms in which there will be a large number of electron excitations taking place and electron de-excitations taking place, and the same thing will happen in the other lamp also, it will be not feasible by any stretch of imagination to predict which electron is going to get de-excited now and what is the exact electric field which is being created by it. So overall there is so much of randomness here and so much of randomness here in both the two lamps that the net electric field created by the first lamp and the net electric field created by the second lamp, they are going to be in two random phases. Two different phases of course, but the phase will also be random. So maybe the light emitted by both of these lamps at some t is equal to t naught will have some kind of a phase difference, and the light emitted by these two lamps at the very next instant t is equal to t1 will have some other phase difference, and the light emitted by these two lamps at t is equal to t2 will have some other phase difference. So the result is that the light reaching S1 and the light reaching S2 has some random phase difference to start with. Now they have a certain phase difference when they reached S1 and S2, and thereafter some more phase difference is going to get added up, but that phase difference is a fixed number. I know that this phase difference is a fixed number because I have been able to calculate it. So there is a random phase difference, and added to the random phase difference there is a fixed phase difference. Overall the total phase difference between these two waves when they arrive at this point P is going to be random. So you insert a random number here, and this random number will mean that this term will change its value all the time. And this number, how frequently will it be changing? So as frequently as there are electron de-excitations here, so maybe billions and billions of times per second. No clue about that, so we have no clue about that. So in fact the idea is that this random phase will be varying billions and billions of times per second, and that will mean that this resultant amplitude at P will also be varying those many times per second, and our human eyes are just not sensitive enough. So human eyes, what they will see is some kind of average intensity at this point P, which will be average of all those intensities which are present at this point P in 1 second, and therefore there will be no interference. There will be no observable interference. So please keep in mind that superposition is still happening, interference is still happening, but it's varying so fast in time that our human eyes are not able to take cognizance of it. So because our human eyes are not able to understand what's happening, we will say that there is no observable interference, and on this entire screen what you will see is an average intensity. So what do we need to have observable interference? To have observable interference, we want this number. In fact, not this number. Let's start from the intensity. We want some intensity at P that should not vary. So if there is a certain intensity at P, then that should be the intensity at P forever, so that I can choose to see it if I want, using bare eyes or maybe under a microscope or something. I should be able to see that intensity. So for the intensity to be fixed at this point P, the amplitude at P should be a fixed number. Now the amplitude at P will be a fixed number only when delta phi at P is fixed. Now delta phi at P has got two contributions. One, there is a delta phi at P because of the extra path that one of the waves is traveling. So that contribution is anyways fixed. What's the other contribution? The other contribution is the initial phase difference. So the waves that reach S1 and the waves that reach S2 have got a phase difference to start with. If that initial phase difference is also kept fixed, so mind my words, I'm not saying that that has to be 0 all the time. I'm saying let it not be 0. Okay, that's also fine. But then if that initial phase difference at S1 and S2, if you keep that number also fixed, then also the total phase difference at this point P is going to be fixed. So what I want is a source that gives me light, and when that light reaches S1 and when that light reaches S2, it does so in such a manner that the phase difference between the lights incident on S1 and incident on S2 is always fixed. In such kind of sources, so now I have created sources S1 and S2. So you will see that I am speaking about two sources S1 and S2 such that S1 and S2 always have a same constant phase difference with respect to each other. And such kind of sources are called coherent sources. So please keep in mind that coherent sources operate at the same frequency and have a constant phase difference between them. It might be non-zero, it may be zero sometimes, but it has to be constant. Constant phase difference between them. And the phase difference between the sources is labeled as the initial phase difference. So the total phase difference at P, or the total phase difference delta phi total, is actually the initial phase difference which is there between the sources plus the phase difference that gets incorporated because of the path difference. And you have to keep this in mind. So please keep this equation in mind. And in the standard Young's experiment that we have seen here, where there was a plane wave coming in like this, the initial phase difference between S1 and S2 was 0. But that might not be the case always. So they may give you variations where there is a phase difference between S1 and S2 to start with, and then there is some more phase difference coming in because of the path difference. So you will have to figure out the total phase difference between the two waves that are interfering at P in such a manner where you have to take into account also the fact that the phase difference that is going to be included because of the path difference may increase the total phase difference, which means it might be added up to this guy, or may decrease the total phase difference, so it might be subtracted from this guy. So all those cases you have to take care of. But keep this in mind that we need coherent sources. So how do we create coherent sources? So what we do is, in order to create coherent sources, let me take this same figure and show you what we usually do. So what we usually do is we don't take two different sources. We take a single source and we keep it somewhere there, and we keep a biconvex lens such that the source that we have taken is at the focus of this biconvex lens. And then the light beam that hits the biconvex lens is sent parallel to the lens after refraction, parallel to the principal axis of the lens after refraction, and it is this beam that acts like a plane wave, and it goes and hits S1 and S2, and S1 and S2 then start in the same phase. When S1 and S2 start in the same phase, then everything else is how we have discussed it. But there may be another variation of the same apparatus, and that variation is this. Sometimes what we may have is a case of this kind where we keep one source but we keep it elsewhere, and you place the lens like this, the light rays go and they become parallel, and this parallel beam is going to go hit S2 as well as S1, and when it hits S2 and S1, what is going to happen is the waves that are hitting S1, they would have traveled a longer distance. The waves that are hitting S2, they would have traveled a shorter distance. So there will be some phase difference incorporated because of this entire process. So please keep in mind that you will have to take care of that initial phase difference also. So more on that as and when it appears in any of the problems. But then you have to keep in mind that we need coherent sources. So one way to create coherent sources S1 and S2 is to create them using a single basic source. So that is what we will do for all the Young's experiments that we are going to perform.